Thank you, everybody. So today I'm going to go through a short little slideshow just to introduce EnginSoft. We're a key partner in design process innovation. And then I'm going to hand things over to Brant and let him go through our...
Is my screen up?
Yep, absolutely.
All right, awesome. Well, good morning, everyone. It's a pleasure to be able to talk with you today. So this talk, we've entitled it, about the, reaching the tipping point, and we'll explain what that's all about. But another way to look at it is we'll be discussing RecurDyn multi-physics capabilities, and the example we're going to show today is that of a fluid product in a flexible container, and look at some of the issues with transport and direction on the assembly line, and do so in a multi-physics way. Okay, so here we have a little example of some product in a plastic bottle on a conveyor line. So in these kind of situations, basically the engineers need to understand what are the dynamics of the bottles as they move around, and with issues like will they tip over, also what will be the issues of the interaction with the different structures that may be guiding the bottles around. As far as basically scarring things up, and but there can be some other issues as well. So the goal is to optimize the bottle transport time while still having a very reliable process. And if you have a faster transit time, then you can reduce your costs because you can handle more bottles in a given amount of time. But if anything tips over, then you've lost a lot, because then the assembly line may need to be stopped and things fixed up manually. So because this is such an important area, then it's really worthwhile to then spend the time to do a careful simulation. And in this case, a careful simulation requires looking at different types of physics to get the correct answer. And in this case, we're going to talk about quad physics, because we're going to talk about the use of 4 different simulation technologies together. And we'll see that it does make a difference to include all the different aspects of it. And, as you can guess, this will be based upon RecurDyn, and we'll be also looking at Particleworks for the fluid, and that will allow us to understand the surge that may occur due to the fluid moving around when the bottle is under acceleration. And then we're going to use the full flex capability in RecurDyn as well, and we'll be reviewing all that. But this is what we want to get to. So this is the bottle, it's under acceleration, and in this case, this is just a bottle, a rigid bottle. Oh no, this is a flexible bottle, but it doesn't have fluid in it. And in this case, we can accelerate this bottle at an acceleration at 4.8 meters per second squared. And as you can see, the bottle is sitting there calmly on the conveyor belt and not tipping. So then, if this was how the simulation was done, then the engineer may report, oh yeah, we can go up to 4.8 meters per second squared. But then if one actually tried it, in this case, we're slowing down to 4.3 meters per second squared, and even in that case, we can see that by including the fluid as part of the simulation, we actually are able to see that the bottle will tip over at this lower, and it's significantly lower, more than 10% lower velocity, and the bottle is in fact tipping over. So then, with more iterations, then one can find, here we're going to repeat it again. In this case, we have actually smaller particles, and in this case, at acceleration of 4.2 meters per second squared, the bottle is able to maintain its position on the conveyor and not tip over. So from 4.8 to 4.2, that's quite a significant difference that we see because of the multi-physics. So the rest of the presentation, we're going to review then how we were able to get to having this model that could do the 4 different types of physics together. We'll also talk about some best practices when doing this kind of multi-physics simulation. We'll talk about the solution approach, and then we'll summarize. So, as background to get into multi-physics, really the first multi-physics was fluid structure interaction, or FSI. And FSI is simply the combination of finite element analysis for the structures and then computational fluid dynamics for the fluid. And, the graphic on the right shows a basic case where the flow is bending this, basic beam structure that's sitting there upright, and it gets bent over due to the fluid flow. And so it's a situation where, you can't really do things separately because the flow is going to deflect the structure. And then as the structure deflects, then that will influence, how the flow is happening. So they interact with each other. So that's why you need to have some kind of a co-simulation. You need to simulate these things together and, carefully look at what the effect of one type of physics, has on the other type of physics, and backwards as well. And so basically seeing the utility of doing this multi-physics, I mean, there's a variety of software packages that have enabled some level of multi-physics capability. So basically that involves architecting the software to be able to do this, co-simulation, pass data back and forth, and, whether that's internal to the package or an external co-simulation, I mean, either way is a possibility. But a key aspect is having an open architecture, as well as custom interfaces to be able to have the different technologies working together. And so, the FSI was the first multi-physics. It was just 2 things working together. And people would just say multi-physics and think about 2 things at a time. But actually, with the more modern architectures, it's possible to go with higher than 2 different types of physics. And by doing so, we're able to see interactions that we just couldn't see before at all, and to understand things better than we ever could. So it's really provides a lot of insight into the behavior of a model to be able to do this multiple types of physics. And RecurDyn is one example of software that's been architected to facilitate this level of multi-physics. So in this example, we're going to talk about quad physics. So what are the 4 things? As we see in the figure, multibody dynamics. So that's the RecurDyn architecture supporting that. And then finite element analysis, which is embodied within RecurDyn as far as the full flex module. And then we'll have the co-simulation with Particleworks. And then the control system simulation then is also embedded within RecurDyn with the co-link product. But it could be a co-simulation as well with Simulink. So in our example, looking at the basic conveyor system that we had, that's a multibody dynamics problem, very simple one. But that was done in the RecurDyn multibody dynamics. And then the bottle itself was modeled as a nonlinear flexible body with full flex. And, we could do the nonlinear flexible body with contact, which is key to this. And then the fluid is simulated with Particleworks. And, the key thing about the interface between Particleworks and RecurDyn is that, and with our most recent versions, even with the full flex bodies, nonlinear flexible bodies, our interface is able to support interaction between the fluid particles and the target bodies of interest. So even in this case, when the bottle itself is flexing, that is still interacting with the particles, and all that's taken into account, all the changes to the surface geometry. And so basically, the element faces of the full flex body are used to provide the contact surfaces that the particles interact with. And then a controller, closed loop. So we're looking at outputs from the system, and then using that to determine when the bottle is approaching a tipping situation. And then as that is sensed, then the control system will then provide inputs, in this case to reduce the acceleration, to prevent the bottle from tipping. So when doing the multi-physics, the complexity of what's involved is really depends on what kind of physics you're doing, because that determines what kind of data has to be transferred. So in the case of a controller, if we have some one or a small handful of inputs and maybe a similar number of outputs, that's very easy to understand. It's also very easy computationally to handle that kind of data transfer. But it's where you get the many-to-many interactions, that's where things start to get a lot more complex. And the prime example of that is the interaction between the fluid in the bottle and the bottle structure itself, because the contact surfaces are all the different element faces, so there's lots of them. And then there's, tens of thousands, hundreds of thousands of particles. And so then we have to keep track of all those particles interacting with all those different element faces. But thankfully, all that's automated. So then, and then kind of in between is when we have the bottle, like, interacting with some kind of a guiding wall. Then you have many finite elements interacting with the wall geometry. Okay, so again, all this is automated. Basically, all we have to do is identify, what surfaces are going to be interacting, or what bodies are interacting with the particles, and then all of the element faces are included automatically. So in setting up such a simulation, there are some factors that are very important. One is, how to set up the model in a reasonable way, taking into account the dynamic response. And the dynamic response is important because it influences the time step that's needed to get accurate answers. So basically when you're doing, multi-physics, then whichever, aspect of physics is requiring the smallest time step, then that's going to determine the time step, because we can't allow any aspect of the simulation to not have proper accuracy. So then we want to look and see what these different time steps are. And in some cases, maybe we can make some adjustments, or maybe this is some feedback to us that maybe we need to change the design a little bit. But as far as like time step for the structural analysis, that's really determined by the material properties, modulus, and so forth. The stiffer the structure, then the higher the frequencies that may occur in it, so therefore the smaller that the time step needs to be. And in the case of the particles, particle-based fluid, then the size of the particles determines the mass of the particles, and the frequency type behavior in the fluid is going to be a function of those particle masses. So as the particles get smaller, then the appropriate time step that should be used also becomes smaller. Anyway, so all that should be looked at, and so then basically as you're solving the system through time, then data is being exchanged. And in the case of the Particleworks with RecurDyn, that's automated, and actually that will result in some data, the handshaking, the data exchange being frequent enough to avoid any kind of numerical instability. But one should watch, I mean, in cases where you don't have the fluids, maybe you're just doing something with controls and maybe some other kind of physics, it's important just to make sure that you have small enough time step, and like in the case of a control system, you can determine and set what that handshaking rate is, and just make sure that's sufficiently frequent to avoid the instability. And basically, if you're wondering whether or not the model is set up properly, a good technique is to just try out things with changing some of the parameters, changing the fluid viscosity, changing some stiffnesses, and just making sure that the model is stable even when the definition is maybe a little bit more extreme in some sense. And so the other thing you can do is you can look at the output data and basically run an FFT on it and determine what kind of frequencies are present in different locations in the model, and then make sure that depending on how high the frequencies are, then make sure the time step is appropriate to capture the behavior of those kind of frequencies. Okay, so then when you're ready to put together, your first model, just remember the old adage that you want to crawl, walk, and run with these models. I mean, that's true with multibody models as well. In this case, what the crawl, walk, and run means is that you need to fight off the urge to, just assemble the entire model all at once and just run it. Because when you do that, then the debugging becomes very lengthy, because the run times are long and there's many possible sources of error. So in this case, the crawl, walk, and run is to, first of all, do each aspect of the model separately. So get your multibody dynamics model all assembled and tuned up. If need be, if you're going to have some flexible bodies, just put them in as rigid bodies to start and get everything else set up. And then you can, add things in. So the most time-consuming aspects of these models are going to be the nonlinear finite element bodies, and then also the Particleworks aspect of the model. Those two are going to be the most time-consuming. The control system capabilities are not computationally intensive, and generally the rest of the multibody system is not too bad either. So I would do, get each part tuned separately, get your Particleworks model running by itself, get everything tuned and checked out, get your full flex bodies done separately, and anyway, and then that's all separate. And then when you start to assemble, start with the multibody dynamics model, maybe add in the controls, and then add in the finite element flex bodies, and then last add the co-simulation with Particleworks. And with many of these models, once you start putting in these, all the different aspects of the model, especially the finite element model and the Particleworks CFD model, then you may end up getting models that are going to run overnight, or even longer, maybe even several days sometimes, depending on the length of time that's being simulated. So, eventually you will get there. You want to put that off as long as possible, because, then the time to, tune the model, that whole process becomes very slow and tedious. So that's why you want to do all the tuning of the individual segments of the model first. So in this case, if looking at the controller, we just did this with Colink, very straightforward. We were just monitoring basically the tipping, angular measurement, and the velocity with respect to the direction it was being accelerated. So we could just focus on that particular rotation. And so we just have these two basic outputs that we're looking at, and then we used that information to be able to affect how high the acceleration was. So basically the gains were set, make sure the bottle would not tip over. Nice thing about this interface with CoLink is that this connect icon that we're looking at here, you can toggle that on and off. So this really makes it easy to do this piece by piece approach, because if you want to just not include the controller, you just toggle off that connect icon, and then it's not included in the simulation. So that really makes it helpful to be able to do things separately. And then, this is showing how, the inputs and the outputs are used. So in the left dialog box here, when you have a plant input, so this is coming from the controller. This is information about the, acceleration information. So basically, the plant inputs are numbered. So you just indicate which one you want. PIN is a regular expression, and then you just link it with the plant input number 1. Then as far as outputs are concerned, you can just use any regular expression. So in this case, we can extract out the information that we want and operate on it as we would like to. Okay, then the full flex body, we can actually import the solid and excuse me, mesh the bottle in RecurDyn with the internal mesher, or you could mesh it externally and import the mesh, either way. So in this case, we did a surface mesh because the structure of the bottle is a fairly thin-walled container. So we just did a surface mesh, so dominant with quad elements, and you can set various parameters and do refinements as needed. And then for Particleworks, as you saw with the animations, we started out by filling the bottle with fluid and letting the fluid settle in. And that actually took about the first second of the simulation before we applied the acceleration. So this shows that in Particleworks, you have this inflow entity, to do this fluid source, and you can define, over time, what's the, basically the, volume of fluid that's coming in. And that's really set up by having a definition of the velocity over time, and then also looking at, here we have the ability to move the position of that filling tube over with time as well. Then fluid properties are basic things: density, thermal conductivity, if you're doing thermal analysis, and same with specific heat, but basic viscosity, and then surface tension are the inputs of the fluid itself. There's other inputs that have to do with adhesion of the fluid to the walls that it's interacting with, and other inputs as well, but these are the fluid inputs. And then to define those walls, this is actually within RecurDyn. So in this case, we can create a patch set, and you can basically select the patch set to interact with the particles. So this walls icon, you select that icon and you pick what's going to be included, that the Particleworks will interact with. And besides the sides of the bottle here, we actually had some geometry on the top to function as the cap. I mean, we're not showing the full cap here, but we just put in some geometry to contain the particles, and we'll see kind of how that works a little bit later as well. And then just like with the CoLink, we have this connect option so that we can include Particleworks with in the co-simulation, or not include it just by toggling this connect, so that we can be able to tune things without everything being there. And then the second one is the second icon. We export the walls, and then we get a wall file, and then this wall file refers to a bunch of object files. And then the wall, but the same, that wall file is all you need to reference to import the geometry from RecurDyn into Particleworks. And so then the geometry comes into Particleworks, and it's understood to be interacting with the particles correctly. And then for post-processing, we've been showing velocity contours. So this is just showing how that's done. You just select the particle contour icon, and then you set in this pull-down menu I'm pointing to right now, you set what attribute of the particle that you want to display. So in this case, we're going to look at the translational velocity and look at its magnitude, but there's many options you can pick there. And so then it will colorize the particles based upon, whether it's at the min or max of the range of velocities in this case. Okay, so what we've just explained is, lets you know how we got to having this quad physics model, and all the different steps that were involved with it. So this is the same animation we were looking at before, but now you can see, how this, the filling tube is raising up and shooting out with certain velocities. And then you can see, with the particle size definition and so forth, determines how many particles are going to, be ejected over time and how many included in the model. And then on the plot on the right, we're looking at the red is the velocity. So we start out with no velocity, then at 1 second, we're assuming that things are settled down, the particles are settled. And then you can see how the surface of the particles went from flat to having this slant to the free surface on the top as the acceleration was applied. And you can see the acceleration being applied starting at 1 second, and then it's ramping up because of the function. I don't know if you remember that function, but there was a step function, ramped up the acceleration, but then in a certain case, then the interaction with the controller, then brought it to pretty much a steady state value, but you can see some a little bit of chatter in the acceleration value because you have some effects, minor effects of the the fluid is still moving, even though the free surface looks pretty stable. The particles themselves are still rocking back and forth a little bit within their own space. So that's just kind of reflecting some of the momentum that's still there in the bottle. So now we're going to look at some different types of scenarios with the bottle. So in this case, we only see the particles, but we're going to impact a wall. And then you can see as the impact occurs, you can see the rest of the bottle enclosure just because of how the particles are limited in their motion as they slosh around. So clearly this impacting the wall is a fairly dynamic event, and you can that's reflected in how the sloshing is going all over the place. Okay, so now we're going to compare things to say, okay, what kind of stresses are we going to see in the bottle? Well, in this case, we're looking at we're still looking at the fluid and the velocities. But then what's that like at 1 meter per second when we hit the wall versus 1.5 meters per second? So the one on the right is going to have the faster velocity, so we would assume more energy when we hit the wall. And in fact, that's enough energy for it to rebound and tip over. So watch that one more time. So again, 1 meter per second it hits, sloshes, but remains upright. But 1.5 meters per second, it's too much energy on the rebound and it tips over. And again, the fluid sloshing, is contributing to the tipping. Okay, so in this case, in both situations, we're going to have impacts at 1 meter per second. But in the left, we have the base case where we have the standard modulus. And on the right, we're experimenting to say, well, what if we reduce the Young's modulus of the bottle by 50%? How does that influence, the stresses seen by the bottle? So you can see, the kind of the pressure wave going through the bottle due to the impact and stresses distributing. So in looking at these animations, we can see that it seems like, I mean, these are consistent scales, so it seems like there's less, red as we're looking at the animation, but not so easy to compare. So really the best way to compare is to take each animation and, find the frame that shows kind of the worst case as far as the stresses are concerned, and then compare those two cases. So what we can see is that the bottle with the reduced Young's modulus does show lower stresses because the deformation can, kind of spread itself out a little bit more effectively and not be concentrated. But, again, quad physics, many different factors. Sometimes the results are a little bit different than what we might expect because we're not anticipating some of the interactions between the different types of physics. So we get a lot of intuition. So this is comparing with the reduced Young's modulus as far as what the fluid's doing. So you can see there are differences on the fluid behavior. How would we describe these differences? I mean, there's different things you can look at. You can look at what's happening with this jet that shoots up. The other thing is you could be studying, velocities throughout. Anyway, there's many things that can be looked at. It is possible to do cutaways and so forth to kind of understand what the particles are doing in different depths of the fluid. Okay, so here we're actually just showing the fluid motion and showing stresses. Of course, the fluid's covering, where some of the stresses are occurring. So there's really a lot of different ways to post-process, visualize the results, and actually it's well worth it to spend the time to do all this post-processing to really understand what's happening, especially the first time you're doing this kind of work. And then once you understand, what the key behaviors are, then, maybe it's a combination of kind of knowing, what kind of key animation viewing parameters you want to set as far as the cutaway settings, as well as, what angle and so forth. And then you'll know how to, show things and be able to explain things to people. Second thing is to identify what the key or output values are, such that you can maybe set up to automatically plot those things. So in summary, this quad physics, to do 4 different types of physics at once, it definitely is something that can be done today. And RecurDyn really has great capabilities to support that. Different types of co-simulation can be done, and also open architecture, where we have the application programming interface for the controls, hydraulics type stuff, where you can embed anything you want with that subroutine interface. Co-simulation not only with particle-based fluids, but also the discrete element modeling, the granular type things, through the EDM software, so you can actually look at non-spherical particles interacting. And as we've seen, by including all the different types of physics, we see better model fidelity. So in our basic example, we are able to see that by including the fluid, that the tipping performance was not as good as it seemed like when the fluid was just modeled as a fixed mass. When you do this kind of work, you want to pay a little bit of attention to time step and handshake rate. RecurDyn does a lot to automatically handle this properly, but you still want to at least take a bit of a checking process when you first do a particular type of model, just to make sure that's right. Again, best practice: create and debug each submodel before merging them all together. Best practice is check for high frequencies and make sure your time step's appropriate to capture those behaviors. And just advice to use the right software, which for our community, we can see that RecurDyn already has the right stuff. People who aren't familiar with RecurDyn might be trying to do this and having a tough go of it without having the interfaces like what we have set up that automatically handles so much of the work. And then once you have your model running, you want to check the results in each physics area separately. Make sure that it's making sense, individually, and then start looking at the interactions. And again, the benefit of gaining more intuition as to what's really going on with your product can really be priceless. And so those insights should be noted, and then also you should figure out your own internal best practices and sort of design guides to make sure that people understand, what are the best ways to set the model up, and also what are the key outputs to look at in order to, best understand the key behaviors of the product. So with that, I am done. I hope we can handle questions. Can we, Hannah?
Yeah, we have some time. So I do have 3 questions here from some of our attendees that kind of joined us late. So Michael from Epson was asking, is there a way to batch optimize when testing different speeds or materials?
Yeah, that can certainly be done. So the fact of doing the co-simulations, I show the different toggles with CoLink and with Particleworks. And so, all those things can be set up, and then inside RecurDyn, you can basically do as part of the design study capability, you can set up a number of runs, and then it will go through all those different things. That's one way to do it. You can also do some things. Some of our clients are running things on high performance computing clusters, so it is possible also to write some scripts to do that automation as well.
Awesome. Wonderful. And just in case everybody didn't already know, we do have a question and answer button that you can simply submit your questions to. So I have another one here from Alan at Unilever. He's asking if the FEA solver, does it support contact between flexible bodies?
Yes, it does. So this is the solver that's included inside of RecurDyn. And so it's a nonlinear flex body, and the contact with other flex bodies, well, that flex body can actually, interact with, rigid geometry. And so then in all cases, the contact is using the element faces. And then the flex body to flex body would be one set of element faces interacting with another set of element faces. And actually that was requested. We haven't done it yet, but somebody was saying that it would be really interesting to do, a set of these bottles, colliding with each other basically. Or, you could have one bottle hitting like that wall, as we saw, but then having another bottle following it and then impacting the bottle in front. So that's, yeah, that would be a really interesting thing to do, and yes, we can do it.
Perfect. I have another question from Alex. He's asking what the handshake rate is.
So in the case with Particleworks, basically with every time step of RecurDyn, then it's doing the handshake with Particleworks. In the case of the controls package, you can set it to a certain fixed rate. And you know, on these problems, I'd say most of the time, the handshake rate ends up being on the order of like 1,000,000 times a second, or 10 to minus 6, is the time step between the handshake. So it's fairly frequent, and it works really well. I can remember, kind of some years ago when people were trying to do the controls and computers were slower, and they were doing handshakes of like 10 to minus 2 or 10 to minus 3. And, it wasn't hard to have problems with that. But with these smaller time steps, the much more frequent handshaking, things seem to be very stable.
Wonderful. Thank you for clarifying that for us. I have one last question here. It's from Dave at 3M. He's asking if my control system is in Simulink, can I use that?
Yeah, absolutely. So the interface would look very much the same, and you'll still have this way to toggle, the connection on and off. And yeah, so RecurDyn has supported Simulink for many years, and so feel free to work with us. There's a tutorial and so forth about it. So we can show you all the details of how that's done, but basically you just use your regular Simulink description, and then we have a file that's read into Simulink that will then define everything needed for the interfacing, and it will also give you a RecurDyn nonlinear plant block that you just connect to inside of Simulink, and that's all that's needed for that interfacing. And then all the other interfacing we've been looking at continues to work just fine when the controller is Simulink.
Awesome. Thank you very much, Brant.